Hello student, let's start with the next chapter of our syllabus, that is nothing but what? Magnetic materials. So in this magnetic material, what exactly magnetic materials are here? Might be all of you are well known about this magnetic material. All of you have learned this magnetic material in your 8 to 10 standard. Might be you have learned the magnetic properties, directive properties, attraction properties of magnet. That part already you have learned 8 to 10 standard. Now here under this topic magnetic materials, what we have to learn? We have to learn about origin of magnetism. How magnetism originate in a material, that we have to see. How or which material are said to be magnetic material, and how that material has a magnetic property, that is nothing but a origin. Why that certain material, just like iron, why the certain material just like iron has a magnetism, and for that to understand this, why the gold doesn't have a magnetism that much, why the aluminum doesn't have magnetism, why the copper doesn't have magnetism. To understand this concept, it is very essential to learn origin of magnetism. So to start with this, first of all, origin of magnetism means what? All of you are well known about one basic part about the material. Every material consists of what? Positively charged nucleus at the center of an atom with a negatively charged electrons revolves in circular orbit around the nucleus. So this positive charge nucleus, it contains proton, positive charge, neutron, neutral, and here electrons are revolving around this nucleus in circular orbit. Due to rotation of the electron has a charge, and we know whenever there is a moment of a charge, there is electric current. If you know, you might be all of you know, current can be written as I equal to dq divided by dt. That means what? Whenever charge is moving with the time, dt for time, dq for charge. Whenever charge is moving with a time, then it will produce what? Electric current. By this formula, as electrons are moving around the nucleus in circular orbit, electrons are moving around a nucleus in circular orbit, we can say electron has a charge, so charge is moving around the nucleus in circular orbit, so this will produce a current. Due to charge movement around the nucleus, it will constitute a current, and this type of magnetic moment due to motion of a charge is called as a orbital magnetic dipole moment. So it is magnetic dipole moment, that is said to be orbital magnetic dipole moment. So here the magnetic dipole, or we can say this electron is moving around a nucleus in circular orbit, it will constitute an electric current, and due to this some magnetic moment, dipole moment get produced, that is said to be orbital magnetic dipole moment. And why it is said to be orbital? Because electrons are revolving in orbit, that's why it is said to be orbital magnetic dipole moment. This is the first part. Apart from this, second dipole moment is also there, that is said to be spin magnetic dipole moment. Now why this spin magnetic dipole moment comes? Due to spinning motion of electron, these electrons are revolving around the nucleus in circular orbit, it will give the orbital motion, orbital magnetic dipole moment. Apart from this, electrons spin about its own axis, just like the earth is spinning around the sun. Earth is spinning as well as earth is rotating around the sun. Similarly, electron rotated in the orbit just like earth. Apart from that, they are spinning about its own axis just like an electron, and due to that spinning motion, it has a spin magnetic dipole moment. Due to rotational motion, it has an orbital magnetic dipole moment. If we add these two together, then we get resultant magnetic dipole moment of a material. Resultant magnetic dipole moment of a material we can get by adding these two dipole moment, spin magnetic dipole moment and orbital magnetic dipole moment. We can add them to get a resultant magnetic dipole moment. Now let's go to next topic of this chapter, that is nothing but what? Magnetic moment of an electron revolving around the nucleus in an atom. Just I have told you, magnetic moment of electron, I will add in short, magnetic moment of electrons revolving around the nucleus revolving around nucleus of atom. I will read it. Magnetic moment of electron revolving around a nucleus of atom. That we have to see. For that, just first of all, we are going to find out, under this topic, we are going to find out only orbital magnetic dipole moment. Similarly, we have to find the spin magnetic dipole moment and add them together to get a total magnetic dipole moment. So first of all, we find out orbital magnetic dipole moment. Let us consider this is a, I will write it here at the center. This is a positive charged nucleus. Around this, electrons are revolving in a circular orbit. Around this nucleus, electrons are revolving in a circular orbit. I will make it at the center. So let us suppose it is the center of this. So nucleus is at the center and these electrons is revolving around the nucleus in the circumference of a circle. That is said to be circumference of a circle, means it is performing orbital motion or rotational motion around the nucleus. This is an electron. These electrons are moving, and due to this rotational motion of electron, they have orbital magnetic dipole moment that we want to find out here. So here the mathematical formula for magnetic dipole moment, that is orbital, that was represented like this: m for magnetic dipole moment, suffix orb, that is for orbital magnetic dipole moment, can be given by one formula, that is nothing but what? The formula as they have given, it is equal to product of current into area. Product of current into area, that will give the orbital magnetic dipole moment. Now suppose this electron is revolving with a velocity v around the nucleus, moving with a velocity v, having a mass of m suffix e, and it will take a time to complete one. Start it here, goes around the nucleus, again come back to the same place, and for that time required is capital T. Then we know what is the velocity. Just we know the velocity, or we can find out time period. Time means what? Time equal to distance travel divided by velocity of object. Suppose electron start here, it come again here. How many distance it will travel? It will travel a distance equal to circumference of a circle. That is nothing but what? 2 pi r. Suppose the radius of the circular path is r. Then the distance travel is 2 pi r divided by velocity we have taken, it is v. From this just find out time. Just suppose time we have to find out is t suppose. Then we can take this v here and we have find out t. From this we can find the velocity. So this equation implies that velocity comes here, time goes here. It is 2 pi r divided by t. This equation gives us a velocity of the particle. Is it? Now velocity of the particle is given by this and time is given by this equation, gives the time period. This equation gives the time period. This equation gives the velocity of an electron. Now as we know, the electron is revolving around the nucleus. It will produce what? Current. And we know what is current for. Just I will write it here a little bit this side I will write. So just we will make it here and just we will shift the setup to a little bit this side. So we want to write here, just we want to find out a current. So current is what? I, and is equal to what? Charge divided by time. Charge which get moved divided by time. As electron is moving in this case, what is charge on electron? It is E. Suppose E is a charge on the electron, time period is T. What is the value of T? Just put from this equation the value of T, put this value here. You can write here it as E into 2 pi r. Okay, sorry, the T is in denominator na, so V goes to numerator, this goes to numerator. E into V divided by 2 pi r, that is the current. I equal to EV divided by 2 pi r. Is it clear? EV divided by 2 pi r. Is it clear to everyone? What we have done? We have just put the value of time period. So just time period we have noted down and we have put its value. we get EV divided by 2 pi r. So in your book there is equation 11.9. This is equation 11.9 from your book. Okay, EV divided by 2 pi r. And now the orbital magnetic dipole moment that was given by this formula, that can be written further. I will write here itself. I just we have find out the value of I, put it here, then the area we have to put. So just put the value of I, it is E into V divided by 2 pi r, that is the value of current, EV divided by 2 pi r, value of current, into area. And now here what should we use? Area, it is circular path. What is the area of circle? It is 2 pi r. Sorry, pi r square. So into pi into r square. This r get cancelled with this r. This pi get cancelled with this pi. Okay. So what we get here? Just we get this equation as equal to 1 by 2 E into V into R. 1 by 2 EVR. That we get here 1 by 2 EVR. Just 1 by 2 EVR is the resultant answer. Now suppose I want to find out little bit, just I will erase little bit this part. We'll write some here, some next topic of this I will write here. Suppose I want to find out angular momentum. Might be all of you are well known about. We have seen the rotational dynamics. Angular momentum. So here angular momentum represented by letter capital L, that can be given as L equal to, it is mvr, and it is electron, so it is me into v into r, is said to be angular dipole moment. Angular momentum. It is angular momentum L equal to me into vr. Now just we have find out this m orbital now. So this implies that m orbital equal to, we have to write just in this equation, this part, multiply and divide numerator by mass of electron. So we can write E divided by twice me. See, me is not there, mass of electron. I have divided by me. Now I should multiply the same equation by me. So we will do it me into v into r in this equation. Multiply and divide by me. We get this. Now me into vr. Just look at this. This is nothing but this part. So this is nothing but L. So you can write orbital magnetic dipole moment is equal to what? E divided by twice me into L. So this equation gives us a relation between magnetic dipole moment, orbital magnetic dipole moment, and angular momentum. They are related to each other with a constant E divided by twice me. This E divided by twice me is said to be gyromagnetic ratio. Remember, E divided by twice me is said to be gyromagnetic ratio, and this equation we have written in magnitude. Suppose I want to return same equation in vector form. What can we write? As we know, charge of electron is minus. So we can write in vector form this with a vector sign, minus of this, and L is a vector sign. That is the same equation in vector form with a minus sign. And point to be remember, E divided by twice me is said to be gyromagnetic ratio. Now there is one postulate, some postulates given by Bohr's. Bohr's atomic model is there, that we are going to learn next chapter. That is in that chapter when we learn, at that time I will tell you in detail. There is second postulate of Bohr's atomic theory of hydrogen atom. According to that Bohr's postulate, what is that postulate? I will write it here. Bohr's second postulate says that angular momentum of revolving electron, that is m into v into r, m into v into r. Here it is electron, so me into v into r. This must be magnetic dipole moment must be equal to n times h divided by 2 pi, and that is the Bohr's second postulate. Postulate means what? Condition. So according to Bohr's second postulate, we can write angular momentum must be n times h divided by 2 pi. Now the same equation that we have derived here orbital magnetic dipole moment can be written. Again, just put the value of this L in this equation. We can write the same equation as I will write here. M orbital, in scalar form I am writing M orbital. So instead of L we should write this part we have to put here instead of L. So what we get, E N H, E into NH divide by 2 2s are 4 pi me, 4 pi me. So this is a new formula for orbital magnetic dipole moment. New formula we have derived, and that was given here. M orbital E and H divided by 4 pi me. Now here for first orbit, n equal to 1, this n equal to 1 for first orbit. Second orbit, n equal to 2. Third orbit, n equal to 3, so on. So first orbit, we can write first orbit for n equal to 1, first orbit we can say. But we can write magnetic orbital magnetic dipole moment is nothing but what? Equal to E into H divided by 4 pi me, divided by 4 pi me, and this is said to be Bohr's magnetron. This bracket value is said to be Bohr's magnetron. It is a constant basically because E is a constant charge on electron, H is a Planck constant, 4 is number, pi is constant, mass of electron is constant, so whole thing is constant. That is said to be Bohr's magnetron, and its value is come to be 9.274 into 10 raised to minus 24. This is the value of magnetic orbital dipole moment for first orbit is this. What is the value for second orbit then? What is the value of n? 2. So this into 2, that is for second orbit. Third orbit 3, this into 3, that is for third orbit, and so on. In this fashion we can find out Bohr's magnetron, or we can find out orbital magnetic dipole moment for first orbit, second orbit, third orbit. Why these orbits are there? Because the electron which is revolving, in which orbit that electron is, that must be known. That's why for first orbit n equal to 1 we should put, we have find out. Second orbit put n equal to 2, is 2 into this third orbit, and so on. In this fashion we have to find out the orbital magnetic dipole moment for a electron for different orbits. Now apart from this, here on next page of your this chapter, the next page, what they have mentioned, they have just tried to give us the revision of Pauli exclusive principle. Might be that Pauli exclusive principle all of you have learned in chemistry 11th standard in chemistry. What is Pauli exclusive principle says? Pauli exclusive principle says that no two electrons have same state of quantum number. What are the quantum numbers here? N, L, ML, N, L, ML and MS. These are said to be quantum number. So no two electron in an atom, they should have same all this value. It is not possible to find out two electrons which have same values of this 4. There must be difference, and that was given by Pauli. So it is said to be Pauli exclusive principle. Apart from this, which material has a magnetic properties, that can be decided by their electronic configuration and pair electron. For example, if you consider chlorine, it has given 17 electrons. 17 electrons are there in chlorine, and how they will represent it in electronic configuration? 1s2, 2s2, okay, 1s2, 2s2, 2p6, then 3s2, then 3p5, I think, yes, 3p, yes, 3p5. Just count this electron: 2, 4, 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 5, 17. It comes to be 17. Now in this case, if you consider first orbit is filled, second orbit is totally filled. First orbit 2 electron, second orbit 8 electron, third orbit, see, 5 plus 2, 7 electrons are only. So third orbit is incomplete, and apart from this, Number of electrons here are odd in number. 5 plus 2, 7. 7 is an odd number. So whenever there is an odd number of electron in last orbit, that particular material has resultant magnetic dipole moment. So just consider this third orbit only. All these first and two orbits are filled. So we are not going to concentrate on this. Concentrate on this last orbit of the atom. So what we can write for 3s2, just I will write here spin. So this up part and this down part. So up one electron, down one electron. Two electrons are over. Then 2p5 we have to consider. For that, this is for 3s. This 3s I have written. Then 3p we have to written. So here it is for 3p first. This is for second and that is for third. So 2p6 are there basically, but we have 5 here. So one up, one down spin, 2 electrons, 2 plus 2, 4 electrons, and this is fifth. See, their spin may get cancelled here also, but this spin can't get cancelled. That's why this material, just like chlorine, they have resultant magnetic dipole moment. Same manner you can apply the same concept to iron, zinc, helium, boron, nickel. Because this unpaired electron is there, then that material have a magnetic properties. And if it is odd, instead of odd it is even number, so there would be another arrow and they get cancelled out. But when there is an odd number, this last arrow never get cancelled out. In that case, that material has a resultant magnetic dipole moment. Same thing they have given on page number 255, right hand side. Observe and discuss the orange color thing they have mentioned. So you have to just take a whole look on that part. Now let's go to next topic of the chapter, and that next topic is nothing but a last topic, magnetization and magnetic intensity. So what is that? Magnetization. Magnetization, Z is there, Z, and magnetic intensity. Magnetic intensity. What exactly magnetization is? What is meant by magnetic intensity? That we have to learn under this topic. What is meant by magnetic intensity and what is meant by magnetization, that we have to learn. So just I have told you there are some material in which the odd number of electrons exist, so that resultant magnetic dipole moment didn't get cancelled out, so that material has some magnetic properties, some non-zero magnetic dipole moment. One of the such material they have given Fe3O4. This is one material, magnetic material, in which there is a resultant magnetic dipole moment, and it is already we have seen. We have find out orbital magnetic dipole moment, that is m orbital we have find out, and when we find out spin orbital magnetic moment, if we add both of them, then we get resultant magnetic dipole moment, m orbital plus m spin. Now here what we have to learn, this material Fe3O4 is a material which has resultant magnetic dipole moment. So suppose this material has net magnetic dipole moment represented by MNET. MNET for net magnetic dipole moment in the material. It is not cancelled out, so it has resultant net magnetic dipole moment, that is this. And if we take a ratio of net magnetic dipole moment divided by volume of that material, that means net magnetic dipole moment divided by volume of that material, it gives the new quantity, and that new quantity is nothing but what? Magnetization. The new quantity is nothing but what? Magnetization. And its vector quantity, it has direction as well as magnitude. Its unit is ampere per meter. It is measured in ampere per meter. It is unit for this, and its dimensions are L to the power minus 1 into A for current. So this is the dimension of this. Dimension in the sense that already we have learned in 11th standard. So dimension, and this is a unit, and this is a formula. Net magnetic dipole moment per unit volume is called as a magnetization. Now apart from this, we have to learn little bit in detail of this magnetization. We have to learn. So let's start with the detail. Just I hope all of you will learn about the magnetization now. Now we have to derive some equations. Suppose we have taken one rod such as a solenoid we have taken, rod of such a material means what? The material like Fe3O4, that rod we have taken, and it is placed in a solenoid having n number of turns. Small n is a number of turns, so it is a number of turn. Now what is meant by number of turns? Number of turns means what? How many windings we have given. Suppose this is a rod and I have taken a wire. One time I have made around it, it is said to be one turn. Two times, two turn. Three times, three turn. That is said to be number. How many times we have given winding to that rod? That is said to be number of turns represented by small n. And let us consider that some current I is flowing through it. Some current I is a current flowing from that particular solenoid which is made up from Fe3O4 material. Now under this condition, what is the magnetic field produced inside this solenoid? What is the magnetic field produced inside this solenoid? That we have to find out. So that magnetic field they have given. So the magnetic field produced inside the solenoid with this n number of turn and I amount of current is passing is equal to mu0 into n into I. N is a number of turn, I is a current, mu0 is called as a permeability of a material, permeability of a medium. Now this much amount of magnetic field produced in a material like Fe3O4 having n number of turn, I amount of current is flowing to this having a permeability mu0. Now suppose what we have done, we have kept such a material inside a solenoid. Now we have kept this material inside a solenoid, then the resultant magnetic field B equal to sum of the original magnetic field plus magnetic field due to material we have kept inside the solenoid, that is Bm. Resultant magnetic field is now B equal to B0 plus Bm. This is a magnetic field without insertion of medium. Fe3O4 we have not kept that in solenoid, only solenoid is there. Then in that case this magnetic field produced inside the solenoid. When we put Fe3O4 material inside the solenoid, the resultant magnetic field is this original, like this original without material plus something after putting the material in the solenoid, B0 plus Bm. Now here this Bm, where this Bm has a value they have given as Bm is nothing but what? Mu0 m. So this is a mu0 into m. This m is said to be magnetization. This magnetization is m. So we can write this equation as, put this B0 from this to this here and Bm from this to this. What we get? B equal to B0 means mu0 n into I plus Bm is what? Mu0 into m. Now in this case if we see mu0 is common, just we can take it common, and here Ni, this Ni is nothing but what? H is said to be n into a number of turns into current flowing through this is represented by one letter, that is said to be magnetic field induced in the material B, and that is represented by H. H is nothing but what? Magnetic intensity. Just see, this is magnetic intensity represented by H. Okay, so this is represented by H, this represented by M. So we can put this value here. So we can write here mu0 is common here and here. This is what? H plus M inside the bracket. That is resultant magnetic field. B equal to H plus M. B equal to H plus M. Again here M equal to, this symbol is there, that is said to be Xi. This symbol is there, that is said to be Xi. So here this symbol is said to be Xi. Here magnetization is equal to Xi into magnetic field intensity H. You can put that value here. You can write this mu0. You can write this as mu0 in a bracket H plus Xi into H. Now here H is common. You can write the same as equal to mu0 1 plus Xi outside the bracket H. Mu0 1 plus Xi outside the bracket, it is H. I will write the remaining to this side. This side I will write. So we get this mu 0 b equal to mu 0 1 plus xi outside the bracket h. But here 1 plus xi as it is, just I will write here b equal to, I will write the remaining part to this side, b equal to 1 plus xi that we have just mentioned here. It is 1 plus xi. 1 plus xi is nothing but a mu r. So mu 0 as it is. This is nothing but a mu r into h as it is. Here what is occur? 1 plus xi is nothing but a mu r, that is said to be relative permittivity of a medium. Again, mu 0 into mu r is said to be mu, permeability of a medium, that is h as it is. So b equal to mu into h, where mu 0 mu r is equal to mu. So if you put that, we get b equal to mu h, b equal to mu h, and that is nothing but what? Resultant answer that we want to find out. So here mu plus mu h we have put this value. So B is said to be magnetic induction, mu is the permeability, h is said to be magnetic field intensity. In this fashion we have find out a relation between this. Below that, just two examples they have solved. Earlier they have solved one example 11.2, now the next one 11.2. Now the point to be remembered is what? This is the chapter we have started, and how many topics we have seen? Just we have seen the two topics. The first, origin of magnetism due to rotation of electron around a nucleus. The orbital dipole moment is there, spin dipole moment is there. That first topic we have seen. Second one is magnetization, magnetic intensity, how they are related by these formulas that we have seen. Now these two topics are there this year due to COVID-19 pandemic year. These two topics would be there for your syllabus, and from this two topic only the question would be asked in the examination. So remember, this is very big chapter. Out of that big chapter, only two topics you have to prepare, and from that two topics and some example, solved example or some example from exercise, what are the formula we have used here? On that formula you have to prepare a numerical. Only two topics and some 4 to 5 formulas are there. On that there would be the examination 4 mark questions. You have to attempt 5 mark questions get asked in examination. Out of that 4 mark questions you have to solve. 5 mark question would be there in examination paper or final board exam. Out of that 4 mark question you have to attempt only on two topic and some 5 to 6 formulas. That's why this chapter is very important. Just prepare only 2 pages and some little bit 5 to 6 type of examples. You get this 4 marks. And this is a smallest chapter made this year, so you should prepare yourself well for this chapter and just try to solve some numerical on this. What type of numericals you have to solve? See, this mu b0 equal to mu 0 ni, one formula is there. Then bm equal to mu 0 m, here I will make it here, bm equal to mu 0 m, second formula. H equal to ni, third formula. M equal to xi h, fourth formula. 1 plus xi is mu r, fifth formula. Then mu 0 mu r is nothing but a mu, fifth formula. So these 5 formulae you have to learn. Gyromagnetic ratio is there, fifth formula. Such a magnet of bhor magnetron is there, seventh formula. On this seventh formula, very few numericals are there. You have to attempt all that numericals and these two topic, and this chapter is finished. So in this fashion we have finished this chapter. In next period we start a new chapter, electromagnetic induction. Thank you.